Howdy, my name is Giselle Gardea and I will be talking about pipeline hazards. Pipeline hazards happen when one instruction cannot immediately follow the next instruction in the pipeline. There are three types of pipeline hazards that occur: structural hazards, control hazards, and data hazards. Hazards can cause many problems in the pipeline by slowing down the instruction execution speed. There is always one solution for these types of hazards, and that is by stalling. But sometimes stalling is not the most efficient way to solve the problem. In this video, I will describe the different ways we can solve hazards efficiently. The first type of hazards are structural hazards. Structural hazards are hazards that occur when there is an attempt to use the same resource by two or more instructions at the same time. There are four solutions to these types of hazards. The first is to, of course, stall the pipeline, but that is not the most efficient way to do it. The other solution is to delay the second access by one clock cycle. The third solution is to provide separate memories for instructions and data, which is not recommended to do. In a real pipeline processor, there are separate caches. As we can see here, we have an example of a structural hazard. Here we have two R-type instructions, add and add, that are using both register 1 to read and write. Even if these two instructions are two instructions apart from each other, there is still a dependency in the pipeline, as we can see here. A way to fix this dependency is to fix the register file to do two things at once: read in the second half of the cycle and write in the first half of the cycle, or vice versa. As we can see in the second example, the load word instruction is reading data from memory, where the third instruction will have to read instruction from memory before it is ready to be used, which is causing a structural hazard. The second type of hazard is a control hazard. Control hazards occur when the destination of a branch needs to be found and can't fetch any new instructions until that destination is found. Solutions for these types of hazards are, of course, stalling the pipeline, stop loading instructions until the result is available, predict if the branch is taken or not taken, assume an outcome and continue fetching the new instructions, a delayed branch, and lastly, specify an architecture that the instruction immediately following the branch is always executed. This ties with the delayed branch solution. Our first example shows the dependency between the first instruction, BEQ, which is a branch instruction, and the load word instruction. Branch instructions will always be executed after the third stage unless specified differently. The next instruction, in this case, the load word instruction, will need the value of the branch before it is ready, causing the control hazard. One of the solutions I described above was to stop loading instructions until the result is ready. This is done by flushing, as we can see on the next slide. Flushing affects the CPU tremendously because it increases the time. As you can see, we had to flush 3 instructions before we have the target ready to be used by the load word instruction. The most efficient way to fix this control hazard is by forwarding. Even though forwarding is more efficient, we still need to flush one instruction, as we can see here on the next slide. The last type of hazard are data hazards. Data hazards happen when reads and writes of data occur in different order in the pipeline than in the program code. These types of data hazards can be further divided into write after read, write after write, and read after write hazards. Solutions to these hazards include stalling, forwarding, and reordering. In this example, we see several dependencies. The first dependency is between the first two instructions, add and sub. They are both using register 1, as we can see here in this example. The second dependency is between the first and third instructions, add and add, that are using the same register 1. The third dependency is between the last two instructions, OR and XOR, with register 1 again. As we see in this next slide, we can fix any data hazard by waiting. We need to stall or wait 2 instructions after the first until the data is ready for the sub and AND instructions to use it. But if we use forwarding, as we can see in the next slide, we don't need to add a stall between those 2 instructions. Any R-type instructions can be solved using forwarding. Forwarding pretty much means taking the data right after it is ready and taking it to where it is needed first. For example, we see in the first instruction, add, we have the value of register 1 ready right after the third stage, which is the ALU stage. In the second stage, we need the value of the first register right before the third stage, meaning in the second instruction, we need it right before the ALU stage. We can just take the data from after the third stage and place it right before the third stage in the second instruction, and this solves the first dependency we stated before. Here's another quick example where 2 types of hazards are present. The first dependency we see in this example is a data hazard between the first instruction BEQ and the third instruction load word, with register 3 being the register that's causing a problem. The second hazard we see is a control hazard with the first instruction BEQ, and because it is a branch instruction. The third hazard we see is in the third instruction load word and the second instruction add, with register 1 causing the problem. The last hazard we see is another control hazard with the last instruction jump, which is also a branch instruction. These hazards were determined by assuming the loop is taken and BEQ, the branch instruction, is not taken. If we want to implement this code in a non-forwarding pipeline, there would be a total of 6 stalls, 3 stalls between BEQ, the first instruction, and add, the second instruction, 2 stalls between the add instruction and the load word instruction, and 1 stall between the jump instruction and going back to the BEQ instruction. That concludes the video. I hope you learned about pipeline hazards and how efficiently to solve them. Thanks for watching.